3. Or if you substitute t into it, you have minus 1 over t minus 3. Then you'd substitute for a, find the limit of it. And when you do, you're going to have the denominator to be 0, and that the one of them is infinite. Now, if one of them is infinite, you see that there were even two components. We are still doing the first one, but we have had an infinity in it. So clearly, you don't even need to continue, because once the first one diverges, you still conclude that it will diverge if even you do the second one. So with this, it's enough to say that the function would diverge. Now, since this integration diverges, it implies that the integral on the left also diverges. Now, equivalently, the integral on the left hand diverges if either of the integral on the right hand diverges. So clearly, one of them diverges, then the original integration itself will diverge. But if it converges, then both of them must converge. So say one converges to a number, the other, then you can add it. But if one of them goes to infinity, then it does not exist. It doesn't have a limit, so it will diverge. Now, in this example, we are integrating the function 1 over x plus 1, 2 over 3. Now, at which point is this function not continuous? This function is not continuous at the point x is minus 1. But the x is minus 1 is in this interval from minus 2 to 7. So we'll have to break it. So x is minus 1, which is in the interval minus 2 to 7. So we have to call our c minus 1. Now, when you find your c to be minus 1, then you write these two integrals. Then you start to integrate them. So if you integrate it using integration processes, now to integrate this, you can use the generalization of what I did earlier on. Now, if you have x plus 1 to the power 2 over 3, you can add 1 to the power. You have 5 over 3, which will be 3 over 5. X to the power 1 to the power 5 over 3. So this is from the generalized power rule. Then, so you add 1 to it, divide by the new power. And when you differentiate this, you get 1. So the integral of this function is 3 over 5 x plus 1 to the power 5 over 3.
Sir.
Yeah. Yes. Oh, okay. It's negative. Sorry. It should be negative. Yes, it's negative because it's in the denominator. So when you add, you're going to get 1 over 3, and this is going to be 3. Okay, so you add, it's negative. You add 1, you have 1 over 3. Everything there, then 3 times that one. Okay, so that's a 3. Then you find the limit of that 3 x plus 1 to the power 1 over 3 t. All this, and then you keep progressing. Now, the first part is 3. Similarly, you can go through, the second part is 6. Then the integral will be the sum of the two of them, the 3 plus the 6, which is equal to 9. Is equal to 9.
Hello.
Yes.
Hello. Please, when you are substituting the limit, we know one is positive and one is negative. You substitute the negative into it, or it is just a representation?
No, there. Are you talking about the left and right limits?
Yes, please. Yes, please.
No, the left and right limit is just to guide you that it's not a complete limit, but it's just a one-sided limit. So if you see t going to -1, it tells you that it's from both sides. But when you see a minus on it, it tells you that the value should be less than -1. So you don't substitute the minus, that other one in it, but it's just to guide you that it's a one-sided limit.
Okay. Okay. Thank you.
So now we have found the first integral. We have 3, the second one is 6, and then you can sum the two of them to get 9. Once you get 9, it tells you that both of them converge, then the integral would converge. Now finally, we've done one now. No problem. So this one too, we have done it already, but let's just do. Now, if f is continuous on an interval a to infinity, then this one we are talking about unbounded intervals. So the first one we did was bounded, but just that either it was not continuous at the A or at the B, or there is a point C where it is not defined. Now, in this part, another place where we use improper integral, apart from discontinuity, is large intervals. Now, we don't know the value of infinity, so we cannot substitute. So if you are integrating something from A to infinity, you don't know the value of infinity. So what you're going to do is that you break it at t, and you find the limit as that t is going to infinity. All right, so the same for the minus infinity. The minus infinity, you're going to find the limit of at a t, but you take the limit as that t goes to minus infinity. Now, just as we said, if you do, and the limit is a number,
It's okay.
cubicle, bits, qubit, mute yourself. Thank you. All right, so if you do, so an improper integral is said to converge if the limit exists, and the limit is the value of the improper integral. If the limit does not exist, then the same hold that it is divergent, or the improper integral diverges. So let's look at some more examples. These ones, we are integrating them from 2 to infinity. From 2 to infinity. Now, what's the domain? The domain is x is 1. So from 2 to infinity, the function is defined everywhere. Just that the infinity part is what we don't know. So to do this integral, we are going to integrate from 2 to a number t, and you find the limit as the t is going to infinity for both of them. For both of them. So clearly, you should be able to integrate the functions. So in this example, we want to integrate 1 over x minus 1 squared dx. Now, to integrate this function, you use the one that we did earlier. So you take the power up, that will be -2, add 1 to it, it will be -1. Then you rewrite it properly. So you're going to have -1 over x minus 1. Then the limit is from 2 to t. So if you do, you're going to have t minus 1, then 2 minus 1. 2 minus 1 is 1. So the second part will be this one. Now, I have -1 over t minus 1 plus 1 over 1 is 1. So it's plus 1. Now, when you find the limit of the first one, as t goes to infinity, you have minus 1 over infinity is 0. So you have 0 plus 1, which is equal to 1. So it converges. That the integral converges and the value is 1. Now, now let's take.
So please, you substituted the infinity for t, and you had
You find
0,
you find the limit.
the limit.
Yes, you find the limit of 1 over t minus 1 as t goes to infinity. As t goes to infinity. Receiving minus, so this one is limit MAT302. So what you do is that you substitute the infinity. Now infinity minus 1 is still infinity, and 1 over infinity is 0. Any number over infinity is 0. You know that 1 over 0 is infinity, and also 1 over infinity is 0. So these are some standard things you ought to have known from the lower levels or from the earlier semesters. Beautiful. Yes. So minus 1 over. Now another thing you can even use how do you call that, asymptotes. That as t goes to infinity, you are talking about the horizontal asymptotes. So the horizontal asymptotes, the numerator is less, the degree of the numerator is less than that of the denominator. So this value will be going to 0. So many ways to do the same thing. So we've done with the first one. Now let's take the second example. So the second example too, we are going to integrate 1 over x minus 1 from 2 to t. No, so this part should be infinity. Then you take from 2 to t and find the limit as t goes to infinity. Now, when you find 1 over x minus 1, you have ln of the denominator. Substitute the values in there. You have ln of t minus 1 minus ln 1. Ln 1 is 0, so you have ln t minus 1. Now, ln infinity is infinity, which means that the integral is equal to infinity, and that one is going to be the integral diverges. If the integral diverges, what do you conclude? That it's an improper integral. It diverges because it goes to infinity. Okay. Now, show that the shaded portion in figure 10 for the function y minus x has a finite region, and compute it. So it's from 1 to infinity. So when you want the area, you're going to integrate the function e minus x dx from 1 to infinity. Now, then the upper limit is infinity, so you're going to integrate it from 1 to t e minus x dx. So maybe let me give you 2 minutes to do this integral. And when we finish, we'll find the limit as t is going to infinity. Okay. So 1 minute to find e minus x dx. Substitute the limit into it quickly. All right, so that is it. Yes, so if you integrate this, you're going to have minus e minus x from 1 to t. So when you substitute, okay, it's all here. For t greater than or equal to 1. So you have from 1 to t, giving you e minus t plus e minus 1. Then you find the limit of it. Now, as t goes to infinity, e minus will be going to 0, giving you e minus 1. Now, e minus 1 is a real number. E to the power minus 1 is a real number. And as you have a real number, it tells you that the function is converging or is finite. It's converging. Now, Gabriel's. Okay, so in the previous example, I wanted to mention this. See that the one with the square in the denominator converges. This one converges, but this one diverges. The 1 over x minus 1 diverges. Now, if you did introductory analysis, you know that, yeah, I'm coming. If you know that there is something called a p-test, I think it's a p-test helps us to know where the function, where to break it and where not to break it. So ratio test and all these other tests, as we have done them. Yes, Tabafo, Mr. Mr. Bafo, your hand is up.
Yes, please. I'm sorry to drag you back. Oh, my network is disturbed.
Yeah.
E raising to the power the infinity, e raising to the power infinity, and the other one also giving us a real number. That means you're going to have two answers, which is one being infinity.
One and what?
Power one is
Okay, let me go to the timed one. Let's see. All right, so I understand that you are talking around this place.
yes. So e raised to the power one is will be giving us a real number. But
Yes.
if you raise the e also to the infinity, we are also going to get divergent.
No, e to the power minus infinity. E to the power minus infinity is not infinite, it's finite, it's 0. It's like this. You write it as 1 over e to the power infinity. You know that these two are the same. Now, 1 over e to the power 0 is infinite. So you have 1 over infinity, and this thing will be going to 0. So that part is a real number. So you're going to have 0 plus the e minus 1. The e minus 1 is a real number. The 0 is a real number. And when you do it, it's finite. So you have that the region has a finite area and it's e minus 1. Okay. So you can bring your hand down now. Thank you. Now let's take an example of the Gabriel's form. Now you have 1 over x, then you have minus 1 over x. The region between the two of them. Now, let f of x be 1 over x. Denote by r the region between the graph f and this. and let D be the solid generated by revolving R about the x-axis. Show that the volume V of D is finite, and show that the surface area S of D is infinite. So the volume is finite, but the surface area is infinite. Now, how do you find the volume of revolution? The volume of revolution. So from fundamental integration, you know that the volume is pi of y squared. The volume is pi of y squared. Now, if you do, and then the graph is starting from 1. So you see that it's from 1, it's starting from 1 here to infinity. So that the volume would be pi times the square of the y from the 1 to the infinity. We're going to integrate it with respect to x. With respect to x. Now, clearly, we're going to have this as required. So you have 1 over x squared, pi 1 over x squared. And when you integrate 1 over x squared, you have minus 1 over x and substitute the limits into it. Now remember that we are summing it to infinity and we cannot sum to infinity. So we have to find the limit as t is going to infinity. So you have from 1 to t. Then as t goes to infinity, you have minus 1 over t plus 1. Plus 1. So when you find the limit of it, you're going to get pi. So the value of the volume is finite. It is pi. But right, so the surface area is given by 2 pi f of s ds. Yeah, Mr. Malcolm.
Sir, please, according to the formula for the volume for the distance, is pi integral from 1 to infinity pi y squared. But we had the distance is 1 over s squared. I didn't understand.
Oh, the function is 1 over x.
S
So
squared.
when you are finding y squared, no, see, the function is here. The function is here, 1 over x.
Y is equal to 1 over. Thank you.
So when you square, it will be 1 over x squared.
Thank you.
Beautiful. Now, let us see. And this is the formula for the surface area. 2 pi f square root of f prime squared plus 1 dx. All right, now, when you go through, you're going to have all these things. So you're integrating from 1 to infinity. But when you do from 1 to infinity, then you have to do from 1 to t. Then you find the limit from t to infinity. Okay, now integrating this function, you can write it as 1 plus x4 all over x4 square root. You can go through the integration methods. Okay, even here, they are using a certain inequality. Now, this value is always greater than or equal to 1 over x. Always greater than 1 over x. So that if you use that and impose it, the value you have will always be greater than 1 over x. Now, this value here is going to ln t. Ln t is equal to infinite. But what you're expecting is should even be greater than this value. So clearly, the surface area of S would be infinite. Okay. Once it is infinite, it tells you that the surface area does not exist. So an improper integral may have two infinite limits of integration, two infinite limits. Now, when you are integrating from minus infinity to infinity,
Okay.
yes,
I would like to see the surface area formula again.
oh, that one is a standard from MAT302. So I was supposed to quote it and use it. So it's here. 2 pi f of s ds. And the ds, if you recall, when you are changing parameters, you have to use the square root of the f prime squared plus 1, the square root of all that. That would be ds. Okay, that is how to convert it.
Thank you, sir.
So you have 2 pi f times the ds, but the ds, you know from advanced algebra that it will be the square root of f prime squared plus 1 dx. All that. Surface area. Right, so finally, if you are integrating from minus infinity to infinity, then you must break it at the point from minus infinity to a point A, then from A to another infinite value. Now, you see that the left side is going to minus infinity, so you must treat it as a case we have seen earlier on. So set a t, then find the limit as that t goes to minus infinity. Then the infinity one to set a t and find it as that t goes to infinity. Okay, so provided both of the improper integrals on the right hand converge, then the function converges. Now, if one of them does not converge, then the overall thing also does not converge. Now, note that when you integrate from minus infinity to infinity, it does not mean that the same as when you integrate from t to minus infinity. So when you have from minus infinity to infinity, you must break it at a point. You must break it at a point before you progress. Now, in this example, we want to integrate from minus infinity to infinity 1 over 1 plus x squared dx. So to integrate this function, we would break it at a point. We can break it at 0. So we have from minus infinity to 0 plus from 0 to infinity, the same function. Then we'll find the limit as this goes to minus infinity, and as the upper limit of this one also goes to, we find the limit as it goes to infinity. All right, so we see them here. Let's break it at 0 to go from minus infinity to 0, then from 0 to infinity. You take them one after the other. Now here, when you integrate 1 over 1 plus x squared, you know that you have tan inverse of x from t to 0. So tan inverse of t minus tan inverse of 0. Now, as this goes to 0, now you know that pi on 2 is infinity. So if you want to find a tan inverse of infinity, you have pi on 2, the reverse of it. So this will be pi on 2 minus 0 and is equal to pi on 2. So it is finite. Then we'll do the second one also. When you do the second one also, you have it to be equal to pi on 2. Now you sum the two of them, you're going to get pi on 2 plus pi on 2 is equal to pi. Is equal to pi, and a graph of it is shown here, so that the area under it is finite. Now B, the unbounded region that lies under the graph and above the x-axis may be assigned an area of pi square units. Right, so we've done 1.5 hours. We'll take a break for 10 minutes. We'll come back at 7:45 or 1:20. I may have some internet challenges at 8 o'clock. So, okay, so let's take the 10 minutes break. When we come, we are having challenges, we'll take a decision. But I expect that we may have some internet challenges at 8 o'clock or around 8 o'clock. All right, please, any question before we take a break? So we are on break. We'll be back at 7:44. Thank you.
Hello, Doc.
Yeah, I believe you.
Doc,
Hello,
you say you'll
Doc.
be going back, or what time will you go back for the chapter 3?
Don't worry. I need us to do this one. I needed to do this, and I also need to do the special functions, gamma and beta functions. But I'll go back also to do the surface integral. Once we've done line integral, surface integral is the double integral part of line integral. So I would go back. We should have enough time to do that. I hope so. If not, I don't know, maybe you read it, you have the notes. So, and today is the final day. Let me mention that I said that if we are not able to finish today, tomorrow morning we'll do from 4:30 thereabout to 5:30 or almost 6. Wherever we get to, we will break, because I cannot I may not be able to meet us on Thursday. So we can only do Monday. Wherever we get to, you read the rest. They are all in there. You discuss them amongst yourself, the rest. All right. So we are on break.
Hey, Doc.
7:44.
Doc, have mercy on us. Oh.
No, me, I wish we'll have time to do all, but the time is constrained. Even I'm not supposed to teach on the weekday, like in a certain way, but I have to make time to. So let's agree to these interim arrangements. Thank
Okay,
you.
Doc. So then, we would only need maybe the areas for the first quiz actually, so that we will concentrate.
You see, when you do that, it shows in the other courses ahead. When you do selective learning, so these continuity things that we are doing, they are in courses that you've done already. So you have learned part of them, but these other ones you've left. As you go up, it shows what you have done and what you have not done. Integration techniques, you will say, okay, this one by parts is difficult. You not learn it, but we are using them. So the courses, as we have designed them, they're actually continuous. And these things, you would use them in ODE. I know you are doing ODE alongside, but these other ones, some of them will show up in ODE, both
So what's
integration.
OD, please?
Oh, are you not doing differential equations? 405. Okay, maybe you don't do it, but I know that the math students do it. I don't know if the ICT students do it.
We are doing it.
Yeah.
No, it's only the math students who are doing OD.
Only the math students are doing the part. So all I'm saying is that these things are continuous courses. So if you learn a portion of it and you may pass, but as you go ahead, it will show that you did not learn these other parts. So you have to be abreast with the entire courses, everything. That's as we are studying, and try as much as possible to make meaning of almost everything, so that when you go to, well, this is the last course, but for those who want to pursue advanced education in these things, you meet them later. Right, so we are still back at in 5 minutes time. We'll be back, but we can still be having such discussions in the 5 minutes.
Doc, it's amazing.
Hello, Doc.
Yes, we can hear you.
Yeah. So, but
with the areas that our sister requested for earlier. Beginning of the program, we are made aware that quiz one is supposed to cover the first half of whatever we are doing. Then the end of semester is for the entire course, and then the quiz two is for the second half. But usually it doesn't go that way. That is why we just want to find out, just for revision's sake, if it will follow the trend of the first half being for quiz one and then the second half being for quiz two.
Well, me, what I'll say is that as for the assessment, I'm not so familiar with what would make up quiz one or what to make up quiz two. I can find out from Professor Essel, but to me, once we have done almost everything, you should be able to write almost everything. And I didn't understand that the quizzes are, I think, after the exams or something. I can't even remember.
So that is the quiz too, dog.
Yeah, quiz. Yes, so one is before the exams, one is after the exams. This type
Yes.
of thing. So you must. We are doing almost everything together. So you don't need to do any specification like this one is for quiz one, because just after the quiz one, the exam is coming, and just after the exams, quiz two is coming. So we only have to be, all rounded. Everything is part.
Hello, dog.
Yeah.
Please, can there be something like maybe an assignment for us, so in case of any emergency, such an assignment can be used for our contractors?
Oh, as for assessment, I'm not so sure. So I can find out. Just that you
I think
are
the IT people is not easy.
you see, when you say with the ICT, with that, you need the maths even more than the maths people. This anyone who does IT must be conversant with mathematics. You would appreciate these things as you go higher. Because when you start doing even your codings and your this, you need advanced mathematics to be able to do programmings, to be able to do a lot. All right, so Evans, you are now joining us. We start at 6 o'clock. We mentioned that we will start this class at 6 o'clock, and we have always started at 6 o'clock, apart from the first week. Beautiful. So the break is almost over. A minute more, and then we'll move on. Okay, so let us progress with the special functions. Now, there are two special functions we ought to know about: the gamma function and beta function. The gamma function and the beta function. Now, the gamma function, see, just like polynomials, what is a polynomial? You know that if I see a function like f of x is equal to, say, let me write 7x cubed minus 4x squared plus 1. You know straightforward that this function is a polynomial function. You are able to identify it that this function is an exponential function. When you see no, this one like this, 3x minus 1, exponential function. So based on a certain categorization, you're able to say that this function falls under this category. So also, we have a class of functions called the gamma functions. And the gamma functions are of this form. So the gamma function is the generalization of the n factorial of n factorial, where n is any positive real number. Now, what is n factorial? You know that n factorial means that multiply the number from 1 times 2 times 3 times 4 times 5 up to the last number n. That is n factorial. So if you say 7 factorial, we are talking about 1 times 2 times 3 times 4 times 5 times 6 and 7. So whatever you multiply them to get, that is the factorial of the number. Now, for x positive, we define a gamma function by the improper integral, the square root of t to the power x minus 1 e to the power minus t dt. So, okay, we've not done Laplace function. So the gamma function, gamma of x, is equal to the integral from 0 to infinity t x minus 1 e minus t dt. Now, when you have this function, this is a product. The above function is not defined for all values of x. Now, the gamma function, gamma of x, the gamma function, gamma of x, is defined everywhere except at 0 and for non-negative integers. Now, the integral cannot be easily evaluated in general. Now, this integral cannot be easily evaluated in general, and therefore, we first look at the gamma function at 2 important points. We'll look at it at 1, and we'll look at it at half. Then, we'll use it to extend to find all the other gammas. Now, what is gamma of 1? So, we write the gamma function as gamma x is equal to the integral from 0 to infinity so the gamma of x is equal to t. Let me look at it. So you're going to have Cx minus 1e minus t. Cx minus 1e minus t dt. Now, first, we want to find gamma of half. Now, gamma of half. Now, if x is half, you're going to have from 0 to infinity of t to the power half e minus t dt. Now, this is an integral that we can easily do using integration by parts. So you have to use integration by parts to do this. Now, when you use integration by parts, so you set y to be equal to root t, and you differentiate it. Okay, so by parts, now you know that integral of u dv is equal to uv minus integral of v u. Now, what to do? So you say that let u be equal to t to the power half. Then you differentiate it. You have du is equal to half t minus half dt. And you can. So you use integration by parts. By parts, you have the function as 2 0 to infinity e minus y squared dy. Now there's a standard integral. You can easily integrate it. So this will be all that's by a. So you do and go through all the processes to get tau of half to be equal to root pi. You can take your time and look at the steps.
So, sir, please, the IT student, are we going to write the same questions with the mathematics student?
Danny Slim, what kind of question are you asking? How?
Are we not learning the same thing?
It's not the same content we are learning now.
Oh, there.
All right, so please let's move on before the internet starts breaking. Your question can make the internet start breaking. Anyway, so let's start.
Yeah, sir. Sir, good morning.
Yes, good morning.
Yeah, concerning the question that is Slim asked, I remember last two semesters we were doing a certain math. I think it was this calculus, either vector calculus or something. The math students, it was a quiz. The paper they wrote was different from the IT papers math. So it is something that has happened before. So if my brother is saying maybe because it has happened before, we wrote the same paper with the math students. They wrote a different quiz question, and we also scanned a different question for the IT students. So it's something that has happened before.
That is the truth.
Yes. That's why maybe this time too something like that can happen. That's why maybe he's asking. Thank you.
All right, I'm happy to inform you that your suggestions are being recorded, and we take your comments very serious. We will review them. So we will ask code to probe into this, because when we take a course, we assign it to a lecturer. We expect that the assessments are same for whichever kind of students, social science students, education students, science students, physical, everybody writes the same exams. So if that thing ever happened, then we have to probe into it.
Okay,
So,
that'll be fine.
so we will refer this to code IT to find out what exactly happened at that point. So we'll be happy if you can give us the cause that thing happened for. Yeah. So
Yeah, it's one
So,
of the
that is how the quiz is. Normally, the quiz, all of us solve different questions. I mean, sometimes there are some questions we may solve. Even your college math students may not have the same question. That is one of
yeah,
the assessment techniques. Me, I
yeah.
know.
yes,
Yeah,
The,
so
yes.
that
the,
one,
the, the quiz, the quiz, that's how it is. Not exams. As for exams,
that's
we
how
all
it
write the
is.
same thing. But the quiz, normally, the math students, one of the course, math students would different from what the IT students wrote.
No,
It was one of the calculus, not the exam. It was a quiz.
And
no.
even
If
even
you
if
explain
with the
that,
math
it's
students,
not
we don't write
entirely
the
accurate.
same quizzes. Sometimes some of the
Yes.
questions that come, one person's question one will be different from somebody's question two. So that one is. Yeah.
There was a time the quiz I wrote,
How
my
can you when
questions
we are
were
It
all
is
totally
never,
different.
never true. We all write the same question. It's never true.
The questions are the same. It's just about serialization. Why you're number one will be someone.
Exactly. The questions are the same.
The
They
questions
just
are the
visualize.
same.
It
Just
is
that your
never
number
true.
one will fall in
The
some
way you are
number
saying
10.
the thing, and you say it clearly, we all write the same question, but they serialize
That
it
is
just
it.
like the way they put to WASI
That
and
is it. So that
BCU.
you cannot
The
just
same
be asking your
question,
colleague to
period.
be giving you answers. That is it.
Please, what you are saying is not entirely true. There are some questions I have written and nobody has written those questions. I am a math student.
It's true. It's true. Yes, it's true.
Yeah, that is
All
true.
right. So let me give.
Yes, it's
Please,
true.
can we have the class?
So let me give you a quick background. So sometimes what happens is that we give um to IT, say 50 questions in a pool. Then they say that they will allocate 20 students to each student. So of these 50 questions, somebody may get from 1 to 20. Somebody will get from 30 to 50. Somebody will get, so they shuffle it. So it's not like to say that we all write different questions. Now, that is why we want to also even probe into it to find out. So if what happened is what I'm saying, then it's not a different case, or it's not a big case. Yeah. So even the math students themselves would admit that what each student writes is different from what the other ones write. It's because of this random shuffle thing that the IT does. All right. So sometimes we give them 40 questions, then they assign randomly. Sometimes 20 questions to each student. That's what we have done over the years. But it's not to say that somebody's question is entirely different from somebody's. And then how do we measure the strength of difficulty? So it's
In
not.
fact, UCC is very serious.
Yeah, sir. Maybe the person is talking about advanced calculus 1. The advanced calculus 1 we did ours last semester, and then they also did this the block 2 rather. So the questions were different because
So if what you're saying is a
it cannot be the same because they did it in second semester and we did it in the third semester.
maybe
Probably you can't have the same question.
Yeah, so it can't be that we'll give you the same questions after these people have done it a semester earlier. It's not done anyway.
he's talking about that one.
Yeah. So
apart
if
from
that's
that
what
all the questions that we are doing is the same thing.
It would be the same. But if you have taken a course in a different semester, you don't expect that we give you the same questions a semester later. But we refer to code and code IT to tell us, at least we are giving us more information into what happened, that they were not even treated in the same semesters. All right, so back to our gamma functions. Now, first, let's start with gamma 1. Now, gamma of 1 means that t should be 0. Now, if t is 0, you have e minus t dt. And when you differentiate e minus t dt, you have e minus t. Then we'll apply improper integral to it. Improper integral means I will take the limit as t goes to infinity. Now, if you do that, you have 1, because the t, you have minus 1 over t, and that will be 0. 1 over infinity is 0. Then you have e to the power 0, which is 1, and then that one is equal to 1, clearly. So you have the gamma of 1 is equal to 1. Now we come to gamma of half. The gamma of half, write it this way. Then we apply integration by parts. And if you do integration by parts, you're going to have 2 e minus y squared dx. Now, you can say that one of them is e minus y squared, and then the other one is e minus x squared dx, the same function, and integrate it. So to integrate this, you can set I squared to be equal to that function squared, which would be this one. Now, integrate this function, it's easy for us to use polar functions from first semester. You know that you say that r squared, s squared plus y squared is r squared. Then the dx dy is r d theta. Then you integrate it by polar integrals. Now, when you go through all of them, you have your I is equal to square root of I over 2. Now, what is I? I is what we represented by one of them. I is e minus that. So, the gamma of half will be equal to root pi. So, gamma of half is root pi. Okay. Now, so also do for the general case. Now, the general case is that if you know gamma of x, you can find gamma of x plus 1. Now, to find gamma of x plus 1, what do? You integrate. You say that ex e minus t dt. Then you do integration by parts. Sometimes you may have to do it several times. But if you do, you're going to have x gamma of x. So this is by integration by parts. I'm not going to go through it. So integration by parts, you keep one of them to be u, the other one to be dv. Then you differentiate the du and you integrate the dv and substitute it into it, so that when you simplify, you have x gamma of x. Now, so 3 things you need to know: that gamma of 1 is 1. We've proved it. Gamma of half is root pi. Then x, gamma of x plus 1 is equal to x gamma of x. All right. Then you can continue. You can continue. Say also that the gamma of x is equal to x minus 1 times gamma of x. So just from the preceding one says that gamma of x is equal to x gamma of, or x plus 1 is x gamma of x. Okay. So if you dummy it and say that I want x minus 1 here, so for every x you set x minus 1, then this will be gamma of x minus 1. Gamma of x minus 1. So let me write it as gamma of x plus 1 is equal to x gamma of x. Then, if I subtract 1 from all of them, I'll have gamma of x is equal to x minus 1 times gamma of x minus 1. So if you know a previous one, you can get the next one by multiplying by x. But if you also know the next one, you can subtract x minus 1 times gamma of that value to get these ones, the previous one. Okay. Now we come to recurrence relations. So first, let's start with the integer ones. So the integer ones, gamma of so you're going to have gamma of, so this is what we've got into. Now first, let's find gamma of 3/2. Now gamma of, you recall that gamma of half is pi. Is it root pi? Gamma of pi is root pi. Now, I want to find gamma of 3/2. And this is the same as gamma of 1 plus 1/2. Now, we just show that if you have gamma of x plus 1, this is x gamma of x. So if I have f of x plus 1, then it means that my x would be equal to half. Then it would mean that the gamma of 3/2 will be equal to gamma half. So by this one will be equal to gamma 3/2 will be equal to half gamma of half. Okay, so if you expand and compare them, you see that your x is half. So you're going to have half of gamma of half. Now, what is gamma of half? Gamma of half is root pi. So that's gamma of 3/2 is root pi on 2. Now, clearly, we can also, in the same way, find gamma of 5/2. Now, gamma of 5/2 will mean that gamma of 3/2 plus 1. And this is equal to 3/2 times gamma of 3/2. Gamma of 3/2. Now, gamma of 3/2 is square root of pi on 2. So this would be equal to 3/2 times the square root of pi on 2, which is 3/4 square root on pi. Okay, so that is 5/2. Now you can also, by extension, find gamma of 7/2, 9/2, and every other one. So what is happening is that you are finding n/2, but the n is an even number. No, it's an odd number. If it's even, then it will fall back into the standard ones. All right, so we'll look at that one also shortly. Okay, so we have 3 pi. All right, so in general, you have gamma of n plus 1 is equal to n gamma of n. All right. So that if you are using the subtraction, combining the two of them, you have n factorial. So let's see here. We know that the gamma of 1 is 1. Now, if you want gamma of 2 will be equal to 2. Is it 2 gamma of 1? Which is equal to 2 times 1. Is equal to 2. Okay, so
But please, can we locate gamma on the calculator?
Thank you. I never
hey,
asked the same question. Yes.
no. Gamma is on
We
the
can.
calculator.
Hey.
Gamma is on the calculator. No, gamma is on the calculator.
So then how did you get gamma of 3 over 2 to the root pi over 2?
I don't get it. Root pi over 2. Oh, we showed that. It's here. So gamma of 3 over 2 is half of. So you bring the x out. X times the gamma of the previous. Okay, so the previous one is like this. The previous one, gamma of half is root pi. So if you want gamma of 3 over 2, gamma of 3 over 2 is 1 plus half. Then the x in this case is half. So you bring the x out and then you do gamma of half. So you have half gamma of half. Now, gamma of half is root pi. So you substitute root pi, you have root pi on 2. Then if you want gamma of 5 over 2, you express it as a gamma plus 1. Now the x in this case is 3 over 2. So you can bring the 3 over 2 out, giving you 3 over 2 gamma of 3 over 2. We know gamma of 3 over 2 already. That is root pi on 2. So you substitute it in it, you get 3 over 4 pi. Then you can continue 7 over 2, 9 over 2, and all the higher ones. Okay.
Thank you.
So we just started with the next one. The next one is gamma of 1, which is the integer values, not the fractional values. Now the integer values, we have gamma of 1 is 1. That one we showed it from integration. Then we want gamma of 2. Now gamma of 2, so this gamma of 2 is not. Now gamma of 2, where is it? From chapter 5. Now gamma of 2, so in general, we have gamma of the next value is n times the gamma of the previous one. Okay, so you can generalize it. Now, in the generalization, you see that the gamma of the previous one is this. So you have gamma of the next one is n gamma of n. Now we know that gamma of n is n minus 1, the gamma of the previous one. Then you do the same thing, n minus 2, gamma of n minus 2, until you get closer and closer to the last one. And the last one is gamma of 1. Gamma of 1 is 1. So before you will have gotten that, you will have had n factorial. So that the gamma of the next one is n factorial. So gamma of n plus 1 is n factorial. So, for example, if we want to find gamma of 7, we'll find 6 factorial. Now, the build-up is like this. If I want gamma of 7, gamma of 7 is 6 gamma of 6. I'm not sure if you appreciate this. So it's x and then gamma of the previous one. Then this would be equal to 6 6 times. Now the gamma of 6 will be 5 times gamma of 5. Then you can do, so you have 6, 5, gamma of 5, 6, 5, gamma of 5. Now gamma of 5 is 4 times gamma of 4. Then, so now gamma of 4. Okay, so I'm going to do it this way: 6 times 5 times 4. Now gamma of 4 will be 3 times gamma of 2. And gamma of 2 will be 2 times gamma of 1. And we know that gamma of 1 is 1. So I see that the gamma of 7 is 6 factorial. So 6 factorial means I'm multiplying the number 6 times 5, or 1 to 6. All right, so that if you know a number, the number is n, then the gamma of the previous number is, the gamma of the number is the previous number factorial. So we're looking at some few examples here. Now, gamma of 7 will be equal to 6 factorial. Gamma of 8 is 7 factorial. And gamma of 9 will be 8 factorial, in that order. Okay. So let us move.
I have then if my understanding, then gamma of 1 will be 0 factorial.
And 0 factorial is 1.
0 factorial.
If you are, yes, you can. That one is on the calculator. So
Okay.
it's an important thing you ought to know. 0 factorial. Where is the factorial? Yeah, factorial is on x inverse. Factorial is on x inverse. So if I do 0 factorial, 0 factorial is 1. So that is also a standard thing that you ought to know in gamma function. But let me mention that you cannot find gamma value, gamma function for the negatives. So that's what we are going to do next. The next one is the recurrence relations, negative values of x. So when x is negative, what do you do? Okay. Now, when x is negative, negative values of x, recurrence relation 4 can be used in the reverse direction as this. So you know that equation 4 says that the gamma of the next one is the number times the gamma of the previous previous number. So if I want gamma of x is f of x plus 1 divided by the x. Now, as x goes to 0, gamma of x goes to infinity. So from this statement here, you know that as x goes to 0, gamma of 1 will be going to 0, which means that gamma of 0 is infinite. And that would also help us to get the gamma of the negative 1 infinite. Gamma of negative 2 is infinite. It follows that for all the negative values, you're going to gamma of them is either positive infinity or negative infinity. But whichever way is negative is going to be infinite. But it is not so for the halves. So if you find gamma of negative half, gamma of negative half is minus half plus 1 divided by the x, which is minus half. And gamma of half is root pi divided by minus pi, and that gives you minus 2 root pi. Then gamma of minus 3 on 2 is gamma of the number divided by the number. So minus 3 over 2 plus 1 over minus 3 on 2. Now the gamma of all that is 4 over 3 root pi. So in conclusion, you are not able to find the gamma of the integer values, but you're able to find the gamma of the half ones. Okay. Now, let us come to the generalization of all. For example, now this function is a gamma function because it has the x exponent part, and then it has also the e minus x dx. Now, the gamma of any number v is given by x to the power v minus 1 e minus x dx. And remember that this whole thing should be equal to v factorial. Gamma of v, no, is the previous one factorial. So it should be v minus 1 factorial. So if I have gamma of 7, remember that gamma of 7 is 6 factorial. So it means that I'm finding v minus 1 factorial. So clearly, if you have x 7 e minus x dx, one of the ways to do it is that you set the power of the x factorial to be the value of the function. So this will be equal to 7 factorial. That is one way to do it. The other way is that we are going to express it as a gamma. So this one we can write it as the integral of x to the power 8 minus 1. Now remember that this value here is our v, or is our value that we are using for the gamma, then e minus x dx. And this thing here will be equal to the gamma of 8, because the v here is the 8. Our v is 8. Now, gamma of 8 is equal to 7 factorial. Okay, so clearly the integral of this function will be equal to 7 factorial. Now, remember that this function, we can integrate it using by parts. Then we'll evaluate it using improper integrals. But when you push it into beta gamma functions, you obtain a direct statement for the value of the integration. Okay, so this is what we have been discussing, that, well, if you have x7 e minus x, write it as 8 minus 1. Write it as gamma of 8 is 7 factorial, and it is 514. That. Now, the next example, we want to evaluate x e minus 4x dx. But the statement is that the e must be to the power minus x. So when you have a function like this and the power on the e is not x, then you have to do the standard substitution. All right, so we're going to make a substitution and say that, well, let's call that whole thing the u. So you say that let u be equal to 4x. It means that x is u minus u over 4. Then you're going to change the base, the variable, into u, and then it will now look like the standard gamma function. And before we now evaluate it, so if you do, you are going to have 1 over 4 to the 4th power u4 minus 1 e minus u du, which is the same as 4 factorial or 3 factorial. So if you do the change of subject, you're going to obtain this one from 0 to infinity. Now, the 1 over 4 constant, then you're going to have gamma of 4. Gamma of 4 is 3 factorial, giving you 6 over 256. 6 over 256 is 1 over 128. Now, the gamma function has a graph like this. So you want to sketch it. Gamma of 0, gamma of half, gamma of 1.
Hello, sir.
Yes.
Kindly go back. Let me observe that solution again.
So we use change of subject. Well, you know that if you transform it into u, you can integrate it in U. You get the same solution. So the problem itself had U to the power minus 4x. Now to make this to the power minus of a value, so we'll say that let's set this to minus U. Then it means that the U is 4x and differentiate it. Then we'll rewrite it properly so that du will be equal to 4dx. Then you would substitute them into it. Now, what is U? U is x is U over 4 cube. So we're going to have U over 4 cube. Then E minus U. Now the dx itself is going to be du over 4. So when you put the 3 u's and the 1 here, you have 1 over 4 to the 4th power. Then you have u to the power 3 e. So this one here is a standard gamma function. So from here, you can know straightforward that this voice from my side. Hello, please, can you all hear me?
Yes, Doc.
Okay. All right, so you write it in the standard form, the standard gamma function form, and then it should guide you in evaluating the standard function. Now, so if you do 0, you have infinity, gamma of half, gamma of 1. When you put all these values together and you plot it, you have a graph like this. And this is a graph of the gamma function. So there would be, how do you call these things? When you see this one going up at this point and this one coming down, it means that there is a vertical asymptote at this point. So at all those points, there will be vertical asymptotes. All right. But we are not interested in those ones for now. But you should be able to write it in a standard form. Then you should be able to pull out your gamma function and should be able to evaluate the gamma function. So we'll be able to evaluate the gamma function for positive integers, evaluate the gamma function for negative integers when it is in the halves or in the integers. Remember that the gamma function of negative integers does not exist, but the gamma function of the fractional ones exists, and we have demonstrated all this. All right, so you should be able to do all these things as we have seen them. Now, quite close to that, it's what we call the beta function. Now, the beta function is coming from the gamma function. So, but the beta function has 2 parameters. So the beta function is 2-parameter composition of gamma functions. So the gamma function is just gamma of certain value x. But the beta function has 2 values in it. The n and the n. All right, so for positive mn, you're going to have this one. Now remember that the gamma function had in it. So the gamma function was like this. You have x to the power b minus 1, e minus t, from 0 to infinity. Then the beta function is like this: x to the power n minus 1, 1 minus x, n minus 1 dx. Now this will converge for n greater than 0, n greater than 0. If both of them are positive, it will converge. But if one of them is non-zero, is non-positive, then, or if one of them is, yes, if one of them is non-positive, it will not converge. Okay. So now the limit when x lies between 0 and when x like the thing. So we're going to do the change of subject. Now, if you do it, to show that the beta function, so you say set 1 minus x to be equal to u. Now, when you do that, your x is 1 minus u. So you're going to have, we want to do a change of subject. If you do that, you have 1 minus u n minus 1, u n minus 1 du. Now, if you rewrite that properly, you have u n minus 1, 1 minus u n minus 1 du. So we started from dmn. Now we have obtained dn because now our first order is n, and then the second one is m. Remember that the order is very important, but we've just shown that the beta function of mn is equal to the beta function of nn. Okay. Now, alternative form of the beta function. Now, the beta function, sometimes we write it as, so let's prove the alternative form. Now, the beta function is given by this. Now, if your differentiation was good, we know from that you can set x to be equal to sine squared theta. When you differentiate it, you have the x is 2 sine theta cos theta d theta. Now, when x is 0, theta is 0. When x, that's the limits. We are changing the limits. Now, when x is 1, we have pi on 2. If the 1 minus x will now be 1 minus sine squared x, which is cos squared x. Okay, so we are going to substitute and transform everything into theta. Then we'll see how it looks like. Now, in theta form, you're going to have two integrals. So the limit will now be from 0 to pi on 2 sine 2m minus 1 theta cos 2n minus 1 d theta. Okay. So that in the polar form, this is the standard one in trig form. Or when we say polar also means trig, or circular is also trig. Okay. Now, the beta is twice the integral from 0 to pi on 2 of sine theta 2n minus 1 cos theta 2n minus 1 theta. Now, you can obtain the gamma function from the beta function, or the beta function from the gamma function. So we're going to look at that quickly. Now, relation between the gamma and the beta function, they are very related. Now, the relation here is that if you say that you have gamma of x, you have gamma of y, then the gamma of x is defined by this, and the gamma of y is defined by this, and you can merge the two of them. So if you merge it, you're going to have this function here. So you're going to integrate double integral from 0 to infinity, 0 to infinity. And then you put the e's together. The e's will be e minus u minus v, u dv. Now, we are going to transform everything to the polar and integrate. So we'll set u to be equal to r cos squared theta, and you set v to be equal to r sine squared theta. Remember that let's do. So then you find the Jacobian determinant. Now the Jacobian means that we are going to differentiate the u with respect to x, with respect to r, and with respect to theta. Then you differentiate the v with respect to r and with respect to theta. So if you do, you're going to obtain this matrix. Then you find the determinant of it. So the determinant of it is going to be equal to what you have here. And you know that the bracket would be equal to 1. So the Jacobian will be 2r sin theta cos theta. So that when we are changing the integral into the polar, you know that the du dv will be equal to the Jacobian dr d theta, where the dr d theta will be determined by the order of the integration. If one depends on the other, you need to consider it first before you integrate the one which have numeral or numbers. So we're going to substitute all this into the gamma x, gamma y. Now, everywhere you see u and v, you put all of them there, and then the du dv. So you're going to expand and simplify. So you expand and simplify. Now, when you expand, you get this term here, the one with the er, the e minus r dr. Now, this is the same as the gamma of x plus y. We have from gamma functions. Then we'll continue to integrate what is in the bracket. Now you have cos of an odd number theta, sine of an odd number theta. So to integrate it, we are going to integrate it by t cos squared theta, integrate it, and then we reintroduce it into the function. So now we'll have this. Now, this would also reduce now to the beta function, so that you have that, well, after you've taken the cos squared theta out, you know that cos squared theta is t, and then sine squared theta is 1 minus t. And this function here is the gamma function, the beta function of x, y. So in general, the beta function of xy is equal to the gamma of x, gamma of y, divided by the gamma of the sum, or the beta m and gamma of m times gamma of n divided by gamma of n plus n, where the standard definition of gamma of x plus 1 is equal to gamma factorial. Okay, so we can replace it back, and once you know the gamma function, you can equivalently also find the beta function of that. Right, so we'll have that the beta function is gamma of m, gamma of n divided by the sum of the two of them. Now this holds even when m and n are not necessarily integers. Okay, now we can use this to prove for the gamma of half. So what you do is that you set your m to be half, you set your n to be half, and then you substitute it into this equation. If you do, you get gamma of half straight. And you know that gamma of half is gamma of half. What is gamma of half? Root pi. Pi. Gamma of half is root pi. Okay, so you go through it, and then you do the substitutions. So you square it. So basically, from here, when you do the half, you have gamma of half plus gamma of 1. Now, gamma of half squared will be pi divided by gamma of 1. Gamma of 1 is 1. So you can pass it through it, and then you are able to establish the fact that gamma of half is equal to the square root of pi. Okay. Now, using this formula, gamma function of fractions of the form, this can easily be calculated. So you can easily calculate gamma functions, fractional gamma functions, using the beta part. Now the remark, the use of gamma beta function in evaluation of definite integral depends largely on your ability to rearrange the integral to be evaluated in the form that is similar to either the gamma function, or you're able to arrange it for it to look like the beta function. Once it looks like the gamma function, the beta function, you can easily progress and then say that this function would be like this. Now in this example, we have I is the integral of x5 1 minus x4 dx. So we can say that this is beta of 4,3. Now remember that the beta function is gamma of the first one. So this will be gamma of 4, gamma of 3, divided by gamma of the sum, gamma of 7. Now when you evaluate, this will be 3 factorial times 2 factorial, 3 factorial, 2 factorial, divided by 6 factorial. Okay, so 3 factorial, 2 factorial, what do you have? So you're going to have the 3 factorial.
Hello, sir.
Yes.
Please, the 4 and 3, where did you get it from? But explain that 4 and 5.
There should be 4 and 5. What is the beta function? The beta function is like this. So gamma of the first value, the gamma of the second value, divided by the gamma of the sum. So if from here, it should be minus 1, minus 1. Okay, so this is how you get it. Now, this one, the powers must be minus 1. So that, okay, so it should be 6 minus 1, and then 5 minus 1. This should be the powers. So let me just make some quick amendments here. So this should be
5, 4.
Should it be 5, 4? No. So it should be 6 beta of 6 and beta of 5. Then you're going to have the gamma of
11.
Divided by that of 11. So this is how it will look like. We're going to have beta of 6, 5. Because you subtract 1 from, you add 1 to each of them to get the m and the n. Then to get the beta of the gamma of it, you have gamma 6, gamma 5 divided by the sum. Now gamma 6 is 5 factorial, gamma 5 is 4 factorial divided by 10 factorial. And then you can evaluate this on your calculator to get this important value. Okay, now in this other example, we have x4, the square root of 1 minus x squared dx. Now we compare this with the standard beta function. Now clearly, what do you see? So we see that we set
Please. Does it mean the other one, that's the final solution, 1 out of 1,060?
Yes, that's the solution of the integral.
But it's very short, that's right.
Yeah, that's it. So the essence of it is another form of integration. But you want to integrate this function. If you want to integrate this function, you should have used by part several times. But you can just move it into gamma functions or beta functions and integrate from there. That's the essence of all these things we are doing today. So if you have this one, now this does not look like the standard one. Now we'll set u to be equal to x squared. So that we'll have the integral of u squared times 1 minus u, then the power is half the u. Now, if you do, you have 2x. Hey, I didn't know right thing. So you're gonna have as a single x squared is equal to y, or y is equal to y to the power half. The x is this, so the limit will be equal to I is half of. So this one will be 2x dx. Then you can bring it out. So this should be over 2. Now you can rewrite it in this way. So please take your time and look at them. All right, so we can rewrite it in this form. Now, so what we did was that we transformed it from, so y to the power minus half. Now, okay, maybe let's do ours. So let's do it together, then we'll establish those results. Square root of x4 square root. So we have the integral of x4, the square root of 1 minus x squared dx, from 0 to 1, I presume. It's from 0 to 1. So let's do it. Now we'll say that let u be x squared. Then the u is 2x dx. 2x dx. Now, we want to write everything in terms of u. So this will be the integral, and the limits, I'll leave them. But if you do, now if x is 0, then you have 0. If x is 1, it will still be the same. Then x4 is u squared times, now 1 minus u squared. So that will be 1 minus u to the power half. So the x squared is u. Now what is the x? The x is the u. Let me write that first. So the x is, so I'll bring the du here. I'll bring the du here. Then we'll have over 2 over 2x over 2x. Now what is x? X is the square root of u. So if I take it up, I'll have u to the power minus half, so that I will not have it in the denominator. Now there is a u here and there is a u here, so I can merge them together. I'm going to have the integral of u to the power 3 over 2 times 1 minus u half du. Now this one, if I change it back to x, you have x 3 over 2 times 1 minus x to the power half dx. Now this is a beta function. What is a beta function? So you have 1 minus half. So this will be beta of 1 half. Then this one will be beta of 1 minus half. So that one will be negative half. All right, so clearly, I'm sure by now you should appreciate.
Yes, Doc.
Yeah, so by now you should see that this should be something like this. So you add 1 to it, and then you have half of the beta All right, so you're going to have half of beta 5/2. So the 5/2 minus 1 is the 3/2.
Oh. But please, you have to do extra calculation.
You see that okay, I've heard. All right, so
But please, we will pay. We will pay. Please, this one here.
it's not about the payment. It's about our availability and your availability, because as we are talking, and we expect 100 students, but only 50 are here. So to me,
hello,
yes.
Doc, please. So, I don't know whether this beta and then gamma function are part of the course outline that we are supposed to learn.
Yes,
for this.
it's part. Yes, it's part.
The other lectures don't have.
Yes, if they don't have, then it means that it's because of the. You see that even what I'm doing now, I have left out the line, the surface integral, but I'm sure that I'll go back to finish it.
Okay.
So I brought it in to make space for the surface integral, which I'm sure that I can also finish within the stipulated time. So when we arrange it, you see that this unit 5, there's even a unit 6, but we are constrained with time, so we have to do unit 1, 2, 3, and 4.
But I want to find out who is the main coordinator for this course, please.
Oh, Professor Esel, his name is on all the sheets.
Oh, okay. Okay, thank you.
You can see Professor EKSL. So, all right. So, I'm sure that we're okay with up to this point. Once you're able to write the beta function, half of that divided by that, and then you have I on 32. Other important formulas. Now, the gamma function of this is given by this asymptotic behavior of the gamma function when n is large. You can assume it to be this one. Now, the last factor, which is very close to 1 for large values of n, you can say that n factorial is this. Then the Stelling's factorial. This factorial is called the Stelling's approximation, or asymptotic formula for n factorial. Okay. Now this also connects sine x, integration of sine functions. So you have it that you have pi over sine pi x. Okay, so there are some few problems here, few more examples here. Now the final one, number 4, is the duplication formula.
Hello, Doc.
Yes.
Let me ask this question before you continue. When we were doing evaluating the beta function, I realized that the limits it's from 0 to 1. Do we have a situation where we may have maybe a different limit aside the 0, 1?
Oh, normally the beta function is standard from 0 to 1. So if it's from 0 to any other function, then you may have to change the limits. And if you change the limits, it's going to affect the functions. Okay, you know that if you are integrating something and then you change the, how do you call that thing, variable, you have to also change the limits. So if you are changing the limits, it will also affect the functions inside it, but it's possible to do it. Okay. All right. So, people, this is some few examples. You can try them on your own. Okay. Now it's almost 9 o'clock. So I'm going to leave out the chapter 3, the surface integral. Then a portion of the Green's function. I think we did some part of Green's function. So I'll come back tomorrow morning. I'll look at the surface integral. I'll look at surface integral, and I'll also do a portion of the Green's function. And I think that should be enough for the course. But anything that we leave out, we have still given you the notes. So we expect that you should be able to do them. So tomorrow morning, please, I'm going to do surface integrals at our usual time, 4:30. Okay. Please, if anyone is up by 4:15, you can notify us to start joining, so that exactly 4:30 we start. Okay. All right. Thank you very much.
Hello, Doc. Hello, Doc.
Yes, we can hear you.
Yeah, please, can you send this slide to the general platform for us, mathematics platform?
Please, your colleagues who have it should appeal to your colleagues who have it to do that, because I'm not on that platform.
Okay.
All right.
Please,
so those
colleague, some of
you
us
can
we don't
just
have it too. Put you in a general this mathematics platform for us. Thank you.
All right. So we'll break here. Tomorrow I'm going to do surface integral. The only difference between line and surface integral is that the surface integral is like multivariate. So you're going to have double integrals coming in, double integrals, and then that's the only difference. So you have a double integral like this, but every other notion stands. So the double integral, so the line integral was like one-dimensional. The surface integral is multi-dimensional. So two surfaces. So you integrate along the x and you also integrate along the y, or you integrate along r and then you also integrate along theta if you're in the polar form, and then all the other ones that. So we're going to do a lot of recall from the first semester, Jacobians, the change of variables from polar to rectangular, from rectangular to polar, and then we'll just apply the formulations, and then we'll be good to go. Okay, so we'll break here. We've done 3 hours thereabouts. We'll come back tomorrow. We'll do 1 more hour. And wherever we get to is time, we'll break. Maybe we can schedule tomorrow. No. I was coming to add tomorrow evening, maybe in the late evenings, say 7 to 9.
That will be okay too. That will be okay too.
But tomorrow we'll meet in the morning. That one, because I'm not sure where I will be around that time, and I cannot be sure about the internet situation. So in the morning, I'm sure about the internet situation, but later in the evening, I don't know. So please, let's be guided. We may organize the evening one. We may not also organize it, but the morning one, we'll come back and do the surface integral and then the grains formulation. And then I think that should be enough. Thank you very much, and do have a good morning, ladies and gentlemen. Bye-bye.
Right.
George, I mean you are there. You will help us to.
Hello, colleague. Those who have the slide, please kindly put it on the mathematics platform for us. Some of us we don't have. Please.
Hey, my brother.
For George, you are
Please,
there.
I hope for tomorrow's morning class, this is the same link we'll be using to join, right? Oh.
I'm sure.
Yeah, it's the same link.
I didn't even get the link earlier. The time I got the link there, Charlie.
Gamma.
Please, kindly, please tell him to give us some sample questions to solve as he did the second semester.
Hey, Madam Eunice, you can solve them.
Yes.
He's not the examiner for advanced calculus.
Yeah, maybe she can solve it.
Oh, you should give us a sample question to solve now.
Me, I was suggesting that if he can give us assignment so that maybe in case of anything, they can rely on the assignment for some control.
It's the second semester, the questions.
If someone give you crowd, only able to
Oh, what is this?
Open
Charlie.
call friend. Why?
Since I started schooling, this is the course I've met, and I'm totally gone. In fact, the man is
You are
just
blank.
trying.
You are off.
I'm just off like light off. Nothing is entering, but the man is just trying his best.
Yes, he's doing well.
Yeah,
He's doing
he's
well
doing
before,
well.
but
He's doing very, very well.
we don't
But it's
have
not,
the basis.
the record is too much, and the record is too much. I never understood integration since
Let, let's
JSS.
let's read with him. You see, second semester, he was the same person that gave us the abstract algebra, the
Yes,
differential
yes,
and
yes.
the vector something. He was the same
Ah,
person.
Yes.
Yeah, so I think we should plead with him
He
so
did
that
well, but this
yes.
one, he is not the coordinator. He is not the coordinator for this one.
Even
The
that
other
one,
one that he gave us the question, he was the coordinator. That is why he gave us the sample questions to solve. But this one,
no,
the
he
professor,
wasn't.
we don't know what he's going to do.
Is the call recorded or it's not recorded?
It's being recorded, but
but if it's recorded, what are we saying? We are not saying anything bad. We are just sharing our
and then
feelings.
even the recording information is meant for us, we the students. They don't take it anywhere.
I think that's the best. If he can provide us with the sample one, he should solve it, everything, and just give it to us.
It's a lot.
Charlie, hey.
The mass people, those who have the slides, please help us with it. The IT, we don't have it. So if you have it, the mass, I don't know how we can get it.
This note he's using,
Yeah.
right?
Yes, please. This
He
is that.
likes push the other one. He likes put the is it a PowerPoint? That is what I pushed to the little bit. But this one I don't have it, so I don't know whether he has shared it with others. I don't know.
I think the mass, they were saying they have it. So please, the mass people, if you have it, let
The
us
mass.
know how best we can get it. Hey, my mass people, nobody's responding to us.
Yes.
Please help us
Yes.
on the slides.
Please, so how can we give it to you unless you give me hi and let me send it to you?
So
on the WhatsApp.
if you put your number here and let me send it to you.
Okay, so I'm putting my number here.
Zero.
Let
me type it in the comment.
Or put your number here and let me send them to you.
Okay. You have my number there.
Are you done now? Are you okay?
Yeah. Once my number is there, I think he's going to send it to me. So I think that is cool.